So now what about data forwarding? This is the idea of getting a result to where it's needed instead of waiting for it to be where it gets put anyway, right? In regular pipelining, before we do data forwarding, we have to wait for the result to be put back in the register file before the next instruction takes it out of the register file. Well, why don't we just give the result to the next instruction without having to wait for it to be done? I mean, of course, we'll still put it in the register file because that instruction's job is to put the result in the register file in the destination register. But at the same time, we're also going to find a way to give it to the next instruction. And giving it to the next instruction means, in a weird kind of way, moving it backwards in the pipeline. Right? The other way to think about this is sort of holding it in place as the pipeline proceeds forward, right? As an instruction proceeds forward, if we just hold the data in place, the next instruction can come into it rather than having to wait for it to be done. So data forwarding allows us to put a result in the place that it's needed so that the next instruction can use it faster before it gets written back to the register file. So what does that look like? We're going to need some additional hardware, right? We're going to need some decisions to be made because when we change any unit, any functional unit in the pipeline, every instruction has to interact with that same functional unit. So when we add pipeline into the ALU, now every instruction has to carry along with it information about am I doing forwarding or not? Am I doing forwarding or not? So we add, again, complexity to the operation. But the result is that we can avoid a no-op or two if we're careful with it. So we're going to implement hardware to do common or likely forwarding tasks. We're going to add connections from the output of one unit back around, sort of backwards, to the input of one unit to allow us to use data before it's ready or before it gets put back where it's supposed to go. Right? And then we need control logic to coordinate between instructions so that we know that this instruction is forwarding to this instruction, but maybe not forwarding in this other way, or maybe this instruction doesn't need to be forwarded. So more decisions to be made. There are limits to data forwarding, right? We cannot go back in time. We cannot predict the future. That's the main thing, right? We cannot predict the future. We can't go forward in time. So there's going to be some time limits that we can't get around, but we will be able to speed things up a little bit. So in the hardware we were looking at a few videos ago, let's look at how we might implement data forwarding if we're going to be doing a register operation right after a register operation, right? This is our original machine. The ALU produces a result and passes it on to the ALU result pipeline latch. But let's allow it to also pass the result back to itself so that I can use that same result again right away instead of waiting. And this is what that looks like. So we pass the ALU result back, right? Data forwarding by going backwards. This is the place where students can sometimes get confused. We're going to pass the ALU result back in the other direction that the pipeline goes and present it to the input of the ALU input latch. And this means that in the next clock cycle, that value from the output of the ALU is presented to the input of the ALU, rather than the value that gets loaded from the register file. Now, we only want to do this in cases where I'm going to use a result immediately right away. But when I do that, I can compress those bubbles down to nothing because I don't have to wait for that result to go past and then stored back in the register file before it's loaded and then presented to the ALU. Now, it's more multiplexers, more choices to make, but that's going to work. And we can add this kind of data forwarding in lots of different stages, right? Maybe it's not this instruction, but the next instruction that needs it. So now we need to forward from after the ALU latch back to before the ALU latch so we can put it in the right time in the right place, right? This is going to get us from one instruction to immediately the next instruction. But if we want to get two instructions from now, then we might have to add a different forwarding hardware. We're going to skip that, but you get the idea, I think. Forwarding, again, is not going to allow us to violate the laws of time or physics. We can only use a result after it's been calculated, but this allows us to use it right away without needing those bubbles, right? So what happens here is in this example, R1 and R2 are added together and the result is put into R0. While this is executing, after the execute phase, before the write back phase, that value, the sum of R1 and R2, it's not an R0 yet, it's just the sum of R1 and R2, it is presented to the execute stage of the next instruction. At the same time, it is written back in the write back stage of the first instruction. So that data is actually split. It's put into two places, right? It's not just forwarded to the previous instruction, but it's also carried on to the next instruction, right? We're still pushing it forward into the ALU result latch at the same time as feeding it back to the ALU input latch. And so that allows the first instruction to complete correctly, which means it's put its result in R0, and it allows the second instruction to operate right away, right? So that's what data forwarding does for us. When we're looking at read after write data stalls, right? Raw data stalls, this is a technique that we can use to fix those, but it means fixing the hardware. Now, it's not going to fix the hardware. It's not going to fix every kind of a stall, right? Let's look at a few examples. Here are a few examples that I will challenge you to pause the video and ask yourself, does data forwarding fix these problems? I'll give you a second to think about it, and then we will go through it, and I will give you the answers, because as you might expect, the answer is not always yes. So you've paused, you've thought about it. It's honestly, it's important to pause and think about it, because when you're learning this stuff, I don't know if this makes sense or not, but videos don't always tell the whole story. And often people who watch videos think they learned something when they didn't learn something. They can't actually do the work, they can just talk about it. So if you actually do it, right, sit down and try it, then you have a better chance of actually internalizing the information and being able to replicate it yourself. So these then examples. This first one is just like what we were talking about before. The only difference is we're using immediate values now instead of register values. Is that okay? Is that going to work? Well, yeah, because the result is aiming for R1. This is the eventual destination, but we can forward it to the ALU again and use it here. Even though you're adding a literal value instead of a register value, that's fine. This will work. No bubbles necessary. What about this second one? Well, what are we doing here? We're loading register R1 with a value from memory at the address calculated by R0 plus 10. In this case, is R1, the value that we want, is it ready after the ALU does its job? Well, no, because the ALU is calculating this effective address. The ALU is not calculating the result of R1, it's calculating the result of the address that will be used to look up R1. And so in this case, we're still going to need those bubbles, right? Maybe a different kind of a data forwarding would work, but not likely, because the load instructions are really the longest instructions, right? The execute unit calculates the effective address, and then the load store unit accesses data, and the result gets put back into the register file. We might be able to take the result from data and put it at the input of the ALU instead of the register file and save one bubble, but data forwarding as we implemented it last time will not solve this problem. Now, what about this one? This one's interesting. BL label. This is branch to a label. This is going to make a choice and decide to go to a different address, right? And then we're going to modify the program counter. We're going to add 17 to the program counter for some reason. So this one changes the program counter. This one also changes the program counter, right? Sorry, it doesn't change the program counter. It just loads the program counter as an input. That should be fine, right? Well, maybe, maybe not, because it depends on if we take the branch or not, right? If we take the branch, this is branch if less. This is a different format than you might be used to for RISC-V or MIPS. But this is going to, the instruction before this will have compared two numbers. And if the result was that one is less than the other, then it'll take the branch. And if the result isn't one that less than the other, then it won't take the branch. And so we don't actually know if this will be taken. And if it is taken, then we're not going to do this instruction. So regardless, we're either going to use speculative execution and just start running this, in which case forwarding the program counter would make sense, or we're going to wait until we know this result, and then forwarding doesn't make any sense because we have to wait for the result anyway. So lots of different places where forwarding might or might not work, but in lots of different contexts, it's going to have lots of different impacts.